Okay, let's take a look at section 4.6 here and the concepts behind it. We're going to do the trapezoidal rule. So we're going to break up our intervals, in this particular case, into equal segments. So I'm going to use my ruler here to break these up into 1, 2, 3, 4 equal segments. And we're going to see what the trapezoidal rule is all about. Okay, so there is my limits. There is going to be my A, and there's going to be my B. And let's refer to these as, let's call this x sub 1, x sub 2, and x sub 3 as the partitions. So let's go ahead and run my input up to the output of the function just to get the height of the function. And what we're going to do now is we're going to do trapezoids from point to point. And we're going to approximate the area under the curve by a sum of 1, 2, 3, 4 trapezoids. Now remember, if we take this to n being infinity, then we're going to get the actual area under the curve. But right now, this is our approximate area under the curve. So let's see how that fits together. So we know if we go here and if we say, well, first of all, we know the area of a trapezoid. Very important to know is 1/2 h times the quantity b1 plus b2, where b1 and b2 are the heights of the legs. Now, we also know that in this particular arrangement, we know that our delta x, okay, is equal to height of our trapezoid. And in this case, then, our delta x is equal to our b minus a divided by the number of partitions. So this would be 1, 2, 3, 4. So n would be 4 for our specific problem, but b minus a over n. And if we go ahead and really just summarize what the rule's about, is the definite integral from a to b of any curve here that's continuous is going to just be f of x dx. But that really is approximated by the summation of the area for all the trapezoids. Okay? So if we talk about it that way, we understand that it's just a geometric representation of what it stands for. So if we just think about this now and just use our formula, it's approximately equal to 1/2 the height, which is delta x. Okay, so let's get that. And if we look at the different values here, notice the left side, which is b1, would be f of a. Okay, and then we would say plus, we would have f of x sub 1. So that would be my b2. But then for the next trapezoid, f of x sub 1 is also my left side, which is b1. So we'll have f of x sub 1. And we'll continue this. Notice for the second one, we'll have for the second one, x sub 2, f of x sub 2 is the right side of that one, but then it's also the left side of the next one. So if we continue this all the way, we'll get to where there's only the end, which would be f of b. Okay, so let's just see how this pans out. For this specific one, we could then just see, okay, it's just equal to 1/2. And we notice then that this is just b minus a over 4 in this case. And we summarize this as being f of a. Then we add 2 f of x sub 1. And then we have 2 f of x sub 2. And you notice we have 2 f of x sub 3. And then finally, we end up with only 1 f of b. So that's going to be our formula that we're going to use. Okay, now this only works when we have even partitions. And even partitions they're hard to come by. They like to see if we know this by making uneven partitions. So the main thing we want to realize is that we have to worry about the formula with the paraboloid. Okay, so let's go ahead and just look at our theorem now and see how it fits together. So the easiest way to remember it now is the estimate for the integral from a to b of f of x dx is just going to be equal to 1/2, and then we have b minus a over n, and then we want to go ahead and write it with f of x sub 0, which is our first term, plus 2 times all the intermediate terms. Okay, and so we'll kind of script this as such, and then we end up with now 2 of f of x n minus 1 for the second to the last term, and then finally we're going to add only one final term in, and we'll group it, and that's how it'll be. Now, we note that if f is concave up, you notice concave up. Here's the concave up part of our curve right here. And you notice we get an overestimate. So it will give you an overestimate. Okay? And if the curve is concave down, notice the region here, and our trapezoids go under the curve, it will give you an underestimate. Okay, so that's important to note there. That'll give you an underestimate. Okay, so when we look at trapezoidal error rule, there is some higher end math that's going on here, and we're not in the scope of our course. We're not going to get into the specifics of it. But we're going to describe this now as that the trapezoidal error rule, and if it's a continuous second derivative, meaning that the second derivative is always defined, then the error, E, in approximating the trapezoidal rule is going to be related by this expression here, that the error here for the rule is going to be less than or equal to the following. It's going to be b minus a, as it's written, cubed over 12n squared. And then what we're going to say is it's going to be the max value of the second derivative of x, okay, on the interval. Okay, so this number here is something we'll need to look at and what the maximum value is. For example, what if this was a sine function? Well, what's the maximum value a sine function can be? And this is the absolute value of the second derivative. So what's the sine value's maximum going to be? Well, 1 at most. But if it's an absolute value, it could be -1 or 1. So we have to look at that. So we're going to look at this, and we're going to see how this will help us out with the error down the road. Okay? So let's kind of remember this. This is going to be b minus a cubed over 12n squared. We're going to remember this rule. Okay, so let's go over and do some examples now. First of all, approximate with the trapezoidal rule using n is equal to 4 subintervals for this problem. We're integrating 0 to pi the sine of x dx. So what we want to do here, first of all, is look at what the curve looks like. So I'm going to go ahead and just rough in the curve. I know that in this interval, from 0 to pi, my sine is always a positive value. So here we have 0 here, and we have pi. They want 4 subintervals. So the first subinterval, if I just split it in 2, would be pi over 2, and this is pi over 4, 3 pi over 4. So these are our 4 subintervals. So this is pi over 4, pi over 2, and 3 pi over 4. Okay, those are our intervals. So it wants to know what the trapezoidal rule. So I'm going to sketch it. So I'm going to go put up one there, one there, one there. And I've got 1, 2, 3, 4 subintervals. So with the trapezoids, this is my first trapezoid. We notice it's going to be an underestimate because in this whole interval, the function is concave down. And you could see that there's gaps. Okay, and if I was using a finer pen, you could see even more gaps. So we're just approximating it. So let's write, remember our approximating. So all we have to do is, since we have even subintervals, we notice that b and let's do this, b minus a over n is equal to pi minus 0 over 4 is pi over 4. So what that means is that's the height of every one of our trapezoids. It's pi over 4. So this is just going to be 1/2, then our pi over 4, and then remember, we only have the first side to remember, so it's going to be f of 0 plus 2 times f of pi over 4 plus 2 times f of pi over 2 plus 2 times f of 3 pi over 4 plus, as I scroll down here, 1 time for the end of f of pi. Okay, so let's go ahead and plug some numbers in. So we have, now if we look at this, we have, it looks like pi over 8, correct? Okay. So let's go ahead with our pi over 8, and we'll substitute values in now. We know the sine of 0 is 0, plus 2 times the sine of pi over 4. So if we look at what is the sine of pi over 4, that's going to be square root 2 over 2, plus 2 times the sine of pi over 2, which is 1, plus 2 times the sine of 3 pi over 4, which we know as square root 2 over 2. Then finally we have 0 for our last term. So finally we put pi over 8, and we add up the numbers. Now we notice here we're going to do a little pi over, or square root 2 plus 2 plus square root 2. And finally we have pi over 8 times 2 plus 2 square root 2. We could factor out a 2 and cancel, and I left with pi over 4 times 1 plus root 2. Okay, so that's going to be our answer, and if we put that in a calculator, that is about 1.896. And that's how we apply the trapezoidal rule to our problem. Now, if we go ahead and find the error, so let's find E sub t, the error, and it's going to be less than or equal to, okay, b minus a, which in this case is pi, and that's cubed, over 12. In this case, we have n is now 4, so it's going to be 4 squared. And then the maximum second derivative. Well, we could look at this and examine. First derivative is cosine. The second derivative is opposite sine. The maximum that opposite sine will be absolute value. It would be a 1. So we could then say our maximum error is just going to be pi raised to the third power divided by 192, and that's going to be equal to roughly 16149. Okay, so that's our maximum error. Finally, let's go ahead and look at the value. And if we go ahead and put that into our calculator, and we see the exact value, remember I'm going to mode and make sure I'm in radian mode. In y1, I'm going to put my sine function. And then I'm going to quit, and I'm going to go math 9. I'm going to go from 0 to pi, and I'm going to do y1, and I'm going to do x for my variable of integration, and you notice I get 2 exactly from my calculator. So the integral, and I could do that this way from 0 to pi of sine x dx is equal to opposite cosine of x evaluated between 0 and pi, and that's equal to opposite cosine pi minus the opposite of cosine of 0. And so if we evaluate that, we know that this bottom term here is negative, and negative 1 is 1 minus a negative 1. So it's plus 1 is equal to 2, and therefore it matches what we have on the calculator. Okay, so that's the first one. We're going to come back and do example 2 in a separate video.